The standard model of particle physics contains exactly 3 generations of chiral fermions, an up quark and a down quark, an electron and its neutrino. That is generation 1. Generations 2 and 3 contain exact copies of those particles, possessing identical gauge quantum numbers and responding to identical forces. But there is a glaring anomaly. This chart displays the 3 generations of fermions, highlighting the mass of the charged leptons. The generation 1 electron has a mass of roughly 0.511 MeV. The generation 2 muon leaps to 105.7 MeV. The generation 3 tau explodes to 1777 MeV. They are functionally identical particles, separated by massive, seemingly arbitrary exponential gaps. To find an underlying structure that predicts these generations, physicists have long looked to the exceptional Lie group E8, focusing heavily on its D4 subalgebra. D4 possesses a unique mathematical property known as triality. It contains 3 distinct 8-dimensional irreducible representations: a vector, a positive spinor, and a negative spinor. Through an S3 outer automorphism, these 3 representations can rotate into one another. They are perfectly symmetric, mathematically equivalent structures. The theoretical application seems obvious. You take the 3 generations of standard model fermions and map them directly onto the 3 symmetric representations of D4, 1 generation for the vector, 1 for each spinor. Mathematical equivalence demands physical equivalence. Any mass term or Yukawa coupling that respects the full symmetry of this structure forces all 3 representations to share the exact same mass. The structural geometry suggests 3 identical generations, but empirical observation proves they are vastly different weights. A static, highly symmetric Lie group framework cannot accurately describe physical reality. This discrepancy reached a mathematical breaking point in 2009 with the Dissler-Garibaldi no-go theorem. Jacques Dissler and Skip Garibaldi proved that extracting 3 chiral standard model generations from a single E8 representation is mathematically impossible without generating unobserved, unphysical mirror fermions. The proof is rooted in strict dimensional constraints and the rigid requirements of anomaly cancellation. If you force the specific chiral demands of 3 standard model generations into the fixed dimensions of E8, the algebra strictly prohibits a clean fit. The proof was definitive. It effectively halted momentum for E8 unification models, pushing the physics community to look elsewhere for a single framework of reality. E8 contains the precise algebraic architecture to house the entirety of the standard model forces, yet rigorous proofs forbid housing all 3 generations of matter within it simultaneously. Mathematical proofs are absolute, but they are only as robust as their initial premises. To bypass Dissler-Garibaldi, we have to examine exactly what the theorem assumes to be true before it begins calculating. The proof rests on the assumption of static representation theory and simultaneous embedding. It assumes E8 is a fixed container. This means forcing 3 distinct generations of matter to coexist inside that boundary all at once. That crowding violates the internal dimensional limits. If we remove the requirement that the embedding must be static and simultaneous, the dimensional constraints of the proof are entirely bypassed. By redefining how representations interact with the underlying algebra, the dimensional counting arguments collapse, and E8 becomes viable again. This requires shifting to the fractal-enhanced timeless quantum substrate hypothesis. Here, the foundational reality is a probabilistic, scale-dependent fractal geometry. We introduce a parameter, S. This parameter dictates the fractal depth, or iteration level, of the mathematics being analyzed. It is a measurement of geometric recursion, completely independent from physical time. At different depths of S, different layers of an algebraic chain become dominant. The chain starts at D3, scales up to D4, expands to F4, and encompasses the full E8. In this framework, E8 functions as a dominant attractor in a higher dimensional configuration space. As the depth parameter S increases, a physical state experiences stronger coupling and gains access to the higher, more complex algebras in the chain. Physical observables dynamically project down through these nested layers. The structural properties we can measure change depending entirely on which fractal scale depth is dictating the projection. The mechanism driving these projections is the fractal inheritance operator. The equation contains two variables, W for scale-dependent inheritance weights and P for specific projection operators. We feed a single fermionic steady state into this operator. At low fractal scales, inheritance weights heavily favor D4 projections. Increasing S shifts weights toward massive F4 and E8 geometries. Because the operator constantly adjusts the mixture of D4, F4, and E8 depending on the scale, it actively breaks the static symmetry of D4 triality in a controlled manner. Therefore, triality becomes a fluid, scale-dependent symmetry. We now have an internal mathematical mechanism capable of differentiating fermion mass at specific intervals without breaking the underlying Lie algebra. We can map these specific intervals directly to the observable universe. Setting the scale parameter to S equals 1 corresponds to generation 1, the electron, the up quark, the down quark. At S equals 1, the seed is dominated by D4's vector representation. Minimal coupling yields the lowest effective mass. Stepping the parameter up to S equals 2 maps perfectly to generation 2, producing the muon. At this step, coupling shifts to F4. The geometry acts as a first harmonic resonance, lifting the effective mass of the state by a universal factor. Finally, we reach S equals 3, generation 3, the tau particle. This scale marks the terminus of the subalgebra chain. At S equals 3, the state reaches its deepest allowed recursion within the E8 structure. The coupling is maximized by the negative spinor representation, yielding the heaviest mass resonance before the algebraic hierarchy is exhausted. This dynamic yields a universal fractal mass scaling law. The mass at any given scale is determined by a baseline multiplied by lambda fractal, a scaling factor that emerges naturally from the product of the coupling weights across the nested geometries. The distinct generations of the standard model are not unique particles. They are the exact same fundamental fermionic wave resonating at 3 discrete fractal depths, generating massive weight hierarchies from pure dynamic geometry. Modulating representations across scales introduces an immediate risk. If the geometric state is shifting, we run the risk of altering gauge charges and failing anomaly cancellation. To prevent this, the projection operators inside the fractal inheritance framework are mathematically constructed to commute with the standard model gauge algebra. A left-handed doublet remains a doublet, and a right-handed singlet remains a singlet. Their chirality is completely undisturbed as the fractal depth increases. The parameter S functions strictly as a dimensional depth index. It is not an internal quantum number, which guarantees it cannot introduce new, unphysical gauge charges into the math. The model operates by pushing one clean projection through varying fractal depths, bypassing the need to cram 3 distinct chiral multiplets into a static box. It preserves precise chirality and evades the mirror fermion trap that killed traditional E8 theory. A mathematical framework that bypasses no-go theorems is useful, but its validity rests entirely on its ability to produce empirical predictions. Because the mass hierarchy follows a specific equation, the universal scaling factor, lambda fractal, must approximate a value of 82 to align with the empirical mass ratio between the tau and the electron. Furthermore, the model demands that the exact value of the electroweak mixing angle can be derived directly from the inner products of the root vectors linking F4 to E8. Even the complex quark and lepton mixing matrices, the CKM and PMNS, emerge as residual triality-induced mixing bleeding across the fractal scales. For decades, the mass gaps separating the electron, the muon, and the tau were viewed as chaotic, frustrating anomalies that defied unified symmetry. They are not accidents. The 3 generations of matter are the clearest signature of a scale-dependent, fractal geometry structuring the foundation of reality.